Good afternoon to everyone. I am not Mark Yanada. Mark Yanada had a big part, I believe, in bringing Keith Nabb to us, our speaker. However, Mark is really sick and has a high fever, so he asked me if I would introduce Keith. And then I met Keith just maybe an hour ago, and Keith said I could pretty much introduce him however I wanted. So that's I met him just about an hour ago, and I thought, seems to be like just a really, really nice guy. And then I saw he had this big stack of heavy-duty math books, and I thought, you know, those are the people you want to watch out for. They seem like really nice guys, but they carry big stacks of heavy-duty math books. In fact, he's traveled today, had to get up really early, traveling alone, but had to rent a van just to house all of those math books.
It's more like a bus.
Or a bus. So, you know, walk softly and carry a bus full of heavy-duty math books. I guess that would be, his story might be a little bit different. You know, I had this great introduction of Keith. In fact, one of the most fantastic introductions ever, but I scribbled what I could in the margin. It wouldn't all fit, so. Keith teaches mathematics at Moraine Valley Community College in Palos Hills, Illinois. He earned his degree from Rhode Island College, Texas Tech University, and Illinois Institute of Technology. Now, this was given to me by Mark. Degrees, yes, degrees, 3 different institutions. So I don't even have a clue how many degrees he has, but I'm sure he's got a lot of them, and they're probably pretty big ones. And his interests include technology and mathematical learning, community college math education, students thinking and reasoning, and traveling around with buses full of heavy-duty math books.
That was not in there.
Oh. So let's give a warm welcome to
All right, thank you so much for inviting me. I've decided after Mark is better, right, because he's really sick, then I'm going to give him a really, really hard time, right, that I had to rent that bus. And now I'm stuck with it for a few days. So I'm going to talk about what I consider a fascinating problem. You guys might have heard a little bit about it. This is Fermat's last theorem. The T is silent, right, so it's Fermat. And so I teach at a very similar institution, Moraine Valley Community College. We're in suburban Chicago, right? So just in Illinois. And so we also have a STEM series and a math club. So it's really awesome to see just how large you guys are really active. And I don't know where you get that great food, you know, so I need to get some feedback on that. All right, so I'm going to talk about this theorem. You may have read a little bit about it. You might know something about it. And so I can't say that I was actively engaged in this theorem, right? But I'm really interested in the history of mathematics. So I'm going to talk about some of the people and the places, right, surrounding this theorem. So this, if you talk to any mathematician, they will tell you this is the most fascinating problem out there. And up until 1994, it was an unsolved problem. So it was an open problem. So definitely the most celebrated theorem in mathematics. It was stated in the 1600s, right? Early 1600s. Scores of mathematicians tried their hand at this problem, but they all failed, right? And this was until the 1990s. And the wonderful thing is I'm going to state it in a couple of minutes, and everyone in the room is going to understand it. In fact, I was explaining this to my 7-year-old, right? So she's just learning about exponents. So I was stating Fermat's last theorem to her, and she understood the scope of it. But the interesting thing is when mathematicians want to make some kind of assertion, when they need to prove something or call something a theorem, that involves a mathematical proof. And that is what was so difficult about this problem, is to actually come up with a mathematical proof and to really call it a theorem. So it's better to call this Fermat's last assertion, right? So it wasn't actually a theorem until 1994. So the wonderful thing, and this relates to the big books I was lugging around, is that this is one of the only known problems in mathematics that connects every single field in mathematics. So you guys probably know a whole lot. The first two fields that come to mind are algebra and geometry, right? But those are distinct fields. But the statement of Fermat's last theorem is a problem that lives in number theory. So this is pretty much arithmetic. It's just understanding numbers, the nature of numbers, why do prime numbers do what they do, right? Things like that. And there are other fields. I was talking to a couple of people who are studying calculus. So in the math world, we call this analysis, right? So there's the study of continuous functions both on the real number line and then on the complex plane as well. So that field is known as analysis. And topology here is a very interesting mathematics where you really study the structure of objects in space, right? And how they undergo continuous transformations. So you're really looking at a geometric structure. And the wonderful thing about this problem, and it wasn't really intentional, is that it actually draws from every single discipline in mathematics. So there's not one of these that isn't represented in Fermat's last theorem. And what we'll find is that this one goes really far back in time. So the claim here is it took 350 years to prove, but it actually, in some sense, might have taken even longer than that when you look at the footprints and the history of the problem. All right, so I'll show you the awesome 5 books. And of course, if you're hanging around later, you can take a look at some of these, right? So this is a geometry book. This is analysis. So if there are any math majors, right, this will torture you in grad school, right? But I write a lot in this book. It's very, very well known. This is an algebra book, and this is not the y equals mx plus b stuff, right? This is abstract algebra. So this is typically a junior or senior level course that you take in college. And then this is where this problem lives, number theory, right? So this is a problem born and bred in that field. And then we have a book on topology. This is one of my favorites, a classic by Moncrief. So basically, if you spent some time investing in this problem, you pretty much have to know everything in these books and a whole lot more. Right? So I'm going to show you some of the names, right, associated with Fermat's last theorem. And these are the modern ones. So you will hear about these people a lot. If you know anything about Fermat's last theorem, you've probably heard of the third gentleman on this list, Andrew Wiles. So the quick story is that Andrew Wiles proved the theorem, right? He's the one that actually solved this, this timeless problem. But it turns out there's a lot of other people that had a whole lot to do with proving this theorem. We will hear a lot about the Taniyama-Shimura Conjecture, right? 2 Japanese mathematicians that came up with this very, very bold conjecture. And Frey here, this modern day Frey curve, right, is a very, very important component of this theorem. And Ken Ribbett opened the door, right, for Andrew Wiles. And Barry Mazur wrote a very, very influential paper in the 70s that more or less without the existence of that paper, all the work that followed, highly, highly questionable, right, if it would have happened. There's a little bit of deception in the story that I'm not going to talk about too much. There is Serre and Freyl, where there was some discrediting, right, of some of the things that happened as the theorem was attempting to be proven. But that's a story for another day, right? This is going to be a happy story, right? Now this is the thing, if you guys have studied lots of mathematics, so now if you look at the historical names that had something to do with this theorem, then you have to say to yourself, you're going to scan this list and you find 4th one down is Euler, and then the 5th one down is Gauss. So I'm done, I'm walking out of here, right? Because most mathematicians will look and they'll say, if you have those 2 mathematicians on the list, these are first-rank mathematicians. These are, without these mathematicians, you wouldn't have the mathematics as we know it today. So Euler was a pioneer in topology, right? That was mainly his thing. Gauss believed that number theory was the heart, the beating heart of mathematics, yet he worked mostly in complex analysis. So Gauss was so incredibly brilliant. Let me make sure I get this right. I believe it was at the age of 15 that he wrote down something like 140 to 150 statements. So they weren't proofs or anything. He just wrote down these statements, and it spanned, I believe, 20 pages. And then if you look at the next 2 centuries of work, so this is 200 years, most of the work that was published in mathematics emanated from those 150 statements. So that is the kind of insight that Gauss had. He was a powerhouse of mathematics. So we're going to see a lot of these mathematicians here and talk about them. The only female you will see on the list is Sophie Germain, right? She actually made leaps and bounds, right, and getting very, very close to proving Fermat's last theorem. She corresponded with Gauss quite a bit, and naturally she had to deal with the prejudice of being a female scientist, so she hid her identity. But Gauss knew it was a her, and he didn't care, right? He said, this woman is worthy of a PhD. Unfortunately, she died before she could be awarded that degree, right? And then we'll see some of the later theories. Kummer and Dirichlet did phenomenal work, not necessarily directly related to Fermat's last theorem, but tangentially. Maybe when I come back, I will talk about Galois, because Galois lived a very, very short life. But a lot of people generally feel the theory that he came up with, which we know today as Galois theory, is perhaps the most beautiful modern-day mathematical theory ever written. And I believe he died at the age of 21. Oh, the things that could have happened, right? Right? So I'm going to state the theorem for you if you haven't seen it before. All right? So if you look at this, just the very top frame, what do you think of? The Pythagorean theorem, right? Right triangles, right? So when we look at this, this statement here is saying that many squares, right, can be divided into the sum of two other squares. We think of 3, 4, 5. I also think of 5, 12, 13. Modern day, we know these as Pythagorean triples, right? That's what they are. So the interesting thing here, the question is, what if we decide to change those 2's, right? Let's change the squares into cubes, right? Let's change them to 3's. And then that becomes a very perplexing, interesting problem. So the statement of Fermat's last theorem is basically if you change that power to a 3, to a 4, to a 5, to any number that you like, you're never ever going to find numbers that satisfy that equation, right? So you can look far and wide, but you're not going to find them. And when we say numbers, we mean obviously non-zero numbers. 0 doesn't count, right? But we're really talking about rational numbers, or we can think simply in terms of integers. So the statement of the theorem is that if you look at the equations down below, good luck. Right? You're never going to find an x, y, and a z. Right? So the informal, I know, you get it, right? It's pretty easy to state. So if you look at the informal way to state this, this is the way we would state it. If n is bigger than 2, in other words, starting at 3, you will never find an a, b, and a c where that equation is true. Never, ever. If you find one right now, you will embarrass me, because then I'll have to go home, right? Now, of course, mathematicians are very sneaky in the way that they state things, because they're not going to state the theorem as you see it in the informal frame. They're going to state it in formal terms here, because mathematicians need to phrase things in a way so that they can actually attempt to prove it, right, to verify the statement. So if you look in a number theory book, you'll find it stated this way. So for n greater than 2, we have the following, right? So they'll call it FLT, case n. And notice what is stated here. A to the n plus b to the n equals c to the n, right? A, b, and c are integers. But what that means is that the product of a, b, and c are equal to 0. So the implication there is one of those is equal to 0. And if one of those is equal to 0, then that basically means the theorem isn't true. Right? You're not going to find numbers that make that true. So you can look at the subtlety of the bottom statement. That is formulated in such a way that you could actually attempt to prove that, right? To show that the product of those 3 would be 0. The one on the top is very ambiguous, because that's indicating you're never going to find the numbers. Well, how do you go about doing that? It's a very, very difficult thing to attack. All right, so I'm going to give just like one slide of historical background, because I can't spend forever talking about this. So this goes back to Babylonian times. I'm going to talk a little bit about Plimpton 322. So this is a Babylonian clay tablet that had, guess what, a bunch of numbers on it. And when they studied the numbers, they found that these numbers were modern-day Pythagorean triples, right? So the Babylonians knew of 3, 4, 5. They knew of 5, 12, 13, right? But they were very, very economical and practical. So they were using these numbers for the purpose of commerce and for building and for construction. And also the Babylonians adored tables, right? So they would just make the tables and say, here we go, we'll do something with that information. So if we fast forward about 1,500 years, right? The Pythagoreans were a very interesting clan of mathematicians. They were like a cult, right? You should read about them. It's very interesting. So, of course, they knew about these numbers as well, but they knew quite a bit more about the numbers. So they knew that the equation x squared plus y squared equals z squared, that in special cases you would get these ordered triples, right, that would actually satisfy that equation. So they were more rigorous in the sense that they proved and they postulated. They also knew of the existence of irrational numbers, right? So they knew quite a bit more about this. And this is where the name comes from, right, for Pythagorean triples. And so they were so profound and deep in their mathematics that if you look at Euclid's Elements, right, the first two books, it's basically all the work of the Greeks, right, of the Pythagoreans. So this is going back way back in time. All right, so now we're at year 250. Diophantus is a preeminent mathematician. Wrote many, many volumes, prolific in mathematics. So of the many, many volumes, just a few of them survived, but it's volume 2, problem 8, right, where Diophantus wrote about dividing a given square into two squares, right? So we're still talking about the Pythagorean theorem here, but this is what caught Fermat. Like, that's a very, very interesting phenomenon. I heard another It's true. I agree. Right? So this is Arithmetica by Diophantus, and Fermat had a Latin translation of this book where he found this remark about taking a square and dividing it into two squares. Right? So now I'm going to show you, this is like the slide of the talk. It's right here. So if you've learned anything about Fermat's last theorem, this is what you know. You've heard about this. So what Fermat wrote, right, what he mentioned here is that when he looked at that statement, he said, on the other hand, you cannot separate a cube into two cubes. You cannot separate a fourth power into two fourth powers, etc., etc., etc. And then this is the line that lives in infamy, right there. I have discovered a truly marvelous proof of this, which, however, right, this margin is not large enough to contain. I don't have enough room. I've got it, but I don't have room. That's where we should be saying, right? But the whole thing is, Fermat was a first-rank mathematician, as E.T. Bell says, and he was a man of impeccable character. He came up with so much deep, amazing mathematics. Occasionally, Fermat would conjecture wrong, but who doesn't? People make mistakes all the time, but he was often right. And he proved a lot, but he left a lot of assertions and conjectures for other people to actually prove. So there's no doubt, maybe he had a proof, right? But this is the interesting thing, is Fermat left many, many bits and pieces of mathematics, but all of them were put to rest, right, by the early 1800s. The only one that was not resolved was this one. No one could quite figure this one out. So this is why it became known as his last theorem. So it should be Fermat's last assertion, the one where he didn't have enough room in the margin. So last year when we had math club, the t-shirt said something like, I have discovered a truly marvelous proof of this, which, however, this t-shirt is not large enough to contain, right? And it had Fermat's last theorem. Okay, so now I want to give you guys a snapshot of what happened, right? What happened after 1637. People are going to tackle this problem and try to figure it out. So the n values here are the powers, right? So n is 3 means we're talking about the cubes. So Fermat himself actually proved it for n equals 3 and n equals 4. Good job, right? And he also recognized that if you could find a solution for a specific n, then it would also exist for a multiple of n. This is actually very easy to show. It's not that difficult to do. Now, Euler completely independently also did it for 3 and 4 via a slightly different method. I believe he messed up one of those, and Gauss stepped in and said, let me fix that for you, right? So Gauss would fix a lot of mistakes. Dirichlet proved it for n is 5, Legendre also, and Henry Lebesgue for n equals 7. Do you see a problem with this?
We're missing a few cases.
We're missing a few cases, right? That's definitely one problem. The other problem, you can see it on the bottom, is 1637, right, is the marginal note. It is now 1840, and we have proved it for 3, 4, 5, and 7, right? But remember, Fermat's last theorem says it's going to be the case for all n. You will never ever find a solution regardless of the power that you choose. So despite the fact that this has been proved by 4 cases, we have a long way to go. Right? So I'm going to talk a little bit about some of the big mathematicians, right, that played a role here. Most of them, some of them indirectly. So this way it'll give you a sense of how the proof went down. So you'll see a little bit about the history. Euler, I mentioned, the most prolific mathematician in the history of mathematics. He did more mathematics, I believe, than anyone else. They're probably still translating some of his volumes. That's how much mathematics he has, right? So he pioneered topology. So he started off with that. Gauss had his hands in everything, as I already mentioned, but it was complex analysis. So informally, complex analysis is basically the calculus that you study, but not with real numbers. It's on the complex plane, right? So you're working with imaginary numbers. Sophie Germain, I mentioned earlier, she actually proved it for many, many primes, less than 100, right? So she made immense progress on this. Fourier, if you know about the Fourier series that bears his name now, this is the infinite series of periodic functions. So it's an infinite series that deals with sines and cosines. It turns out when you generalize that to the complex plane, then we have something where Henry Poincaré did some work on automorphic forms and also modular forms. Now the one I want to spend the most time is Dirichlet. This was revolutionary what he did. It actually had nothing to do with Fermat's last theorem. So he had a problem on progressions, right? So he was trying to prove something in this world of discrete numbers. But what he did is he married the fields. I'm going over here to my books. He married 2 fields. So he was trying to solve a problem in number theory, but he used tools from analysis. And analysis is the study of continuous functions. So why in the world would you need continuous functions to work on something that is like some kind of progression? So he used a tool from a different field to solve the problem. This would foreshadow exactly the kind of thinking that would be needed to prove Fermat's last theorem. So even though this is very common today, it was not common in the early 1800s. So this was considered really something fantastic. Kummer is the main individual here who was totally obsessed with FLT. He wanted to prove the theorem. I mean, I want to prove the theorem, right? So when, in his efforts to actually try to prove the theorem, he found that he needed numbers to satisfy certain properties, right, to actually get the theorem to work. But the numbers never satisfied them. So you know what he did? He invented numbers that satisfied those properties. They are known today as ideal numbers. And so this was generalized later by Dedekind, the theory of ideals. And then this went into some of Barry Mazur's work, which led to Ken Ribbett and Andrew Watt. Now Galois, his Galois theory, as we know it today, was a critical piece to proving Fermat's last theorem. So we'll hear about him again. And as I mentioned, this individual, he was too smart for his own good. He was twice rejected entry to university, mainly because his examiners couldn't understand what he was talking about. He was too smart. So he failed not once, but twice. But when you look at his Galois theory, as I mentioned, this is the most beautiful theory known in mathematics. Abel, you might study the notion of an abelian group, right, when you study abstract algebra. So when you generalize that, you have an abelian variety. That's another component, right, in Fermat's last theorem. And then Poincaré really generalized the work of Fourier. So we're going back to the infinite series of periodic functions. So he studied these things in the complex world, right? So we're talking about I equals the square root of -1. So he pioneered this notion of modular forms. We're going to hear a lot about that because that has a lot to do with Fermat's last theorem. All right, so now look, here we are, right, 1900s. We're almost there. The Germans were getting fed up with this, right? So they're saying it's 1908, we need to give an award for someone who's going to prove this theorem, right? So they put it out there, and the first year, scores of proofs, hundreds of them come, right? And they're coming from professionals, they're coming from amateurs, and of course the common thing is they're all wrong, right? So they're all flawed, and then years go by, thousands more proofs are coming in, but they're all incorrect. So Fermat's last theorem is starting to symbolize the Holy Grail, This is a problem that just can't be solved. No one can do it. Right? I'll talk a little bit about the progress here. You'll notice a huge gap in the years also, because we're accelerating, right? 350 years is a lot to talk about. So, 1922, Mordell made a critical link. So look at this. The trend is coming back, right? Topology and algebra are two distinct fields. What Mordell does, he doesn't prove it, but he makes a conjecture that there's a link, right, between these. And so this is something called the genus. It's really about the number of punctures in a surface, right, the number of holes. So this is a topological construct. So his conjecture here is if the surface has two or more holes, then the corresponding equation has only a finite number of whole number solutions. So when we think of an equation, we think of algebra. But when you think of surfaces, you think of topology. So he was saying there's an intimate link between these two things. However, it was a conjecture, right? He wasn't able to prove it. So Faltings in 1983, that is 60 years later, proves Mordell's conjecture. So the important thing here is not actually the proof of this, but it's the implication of it. So we know that Fermat's equation actually had the genus greater than 3. So what that meant is that if Fermat's equation had a solution for some n way out there, then there's probably only a few that you're going to find, right? There was a finite number of solutions. And another implication of that is as the n value increased, as the power increased, you were less likely to find an ordered triple. So if you were going to find one, you might find one, and that would be it. But notice that would put Fermat's last theorem to rest. That would mean it would be false, right? Because you would find an ordered triple. I like this. That's what it means, right? Fermat's last theorem is almost true, right? So this stuff on the bottom is because of modern computing, right? So the computer scientists got very, very excited about this. All right, I'll run some simulations. I'll do it, right? So we are up to 1 million, right? So we're looking back at Lebesgue and Legendre, right? Just proving it for certain cases. We're up to 1 million. 92. 92 is an important year for me. I won't tell you why, because it'll date me. But, 92 is a good year. 4 million. So if you watch the documentary on Fermat's last theorem, they have a discussion with John Conway, he's professor emeritus at Princeton. And he mentions this like, wow, we got all the way to 4 million. Isn't that great? But how much further do we have to go?
A whole lot.
We basically haven't even started, right? Because Fermat's last theorem is the assertion that it's not going to work for any n greater than 2, right? So really, there's no difference between 1 million and 4 million, right? And you could tell here that this is just not the right approach, right? This is not the way to go. I'll mention one thing is that Faltings, people did feel like he was going to be the one that would prove the theorem. So I might mention him a little bit later. Right, so this is the only time I'm going to shower you with mathematics. So, oh no, right? So listen up, this is very important. This is an important slide, right? Elliptic curves have nothing to do with ellipses, right? They're actually cubic functions. That's all they are, cubics. And if you look at the solutions, right, the rational solutions, the rational points of these curves form something in algebra known as a group. And the solutions here form the shape of a torus, which is like a mathematical donut. So if you look at elliptic curves, this here is really the marriage of, we would say, algebra and topology. So you could see, if you look at that equation, that's an algebraic equation. But if we're talking about the structure of these surfaces, that's a topological construct. So this is a very well-developed field at the time. And down below, we have modular forms. Remember, this was pioneered by Poincaré as he generalized the work of Fourier. Now, modular forms are very hard to describe. They are these objects, right, that live in the complex world. So we're talking about analysis, right, complex analysis. They have a non-standard geometry. So this is the geometry where two parallel lines, it's not the geometry where two parallel lines never meet. This is a hyperbolic geometry. And their symmetries are so incredible that you would need to stretch things out to actually look at all of their symmetries. So if you look at modular forms, this is really, these objects reside in geometry and analysis. So if you look very carefully, you see 4 of the 5 fields represented here. So algebra and topology on the top, and you see geometry and analysis on the bottom. Now the most important thing to note is there's no connection between these at all. These are like 2 disparate, totally weird fields, right? But the only field that isn't up here is number theory, right? That's where Fermat's last theorem lives. It's a number theoretic problem. Well, guess what? Mathematicians were about to discover that these 2 things that are totally different are actually the same, right? So what we're going to see here is that a conjecture came out that all elliptic curves are actually modular forms in disguise. They're sort of hidden, right? So this here was known not as a groundbreaking conjecture, but as almost a crazy conjecture, because it wasn't evident at all that these 2 well-developed fields had anything to do with one another. But that is exactly what one mathematician would conjecture. So now we're September 1955, right after the war, and basically there's a conference in Japan, Tokyo Nikko Symposium. And this was formed mainly by Taniyama and Shimura. And so there were 30 or so statements at this number theory conference, and they reached out and invited some of the best in the world. I'm only mentioning a few of the attendees. There were probably hundreds. So we have Sarah in there and also Veal. So the conjecture here was that all elliptic functions are modular. So if I go back to that, that's the connection between these 2. Right? So we have the elliptic curves and the modular forms. So this was the conjecture made by Taniyama. He had 4 or 5 at the conference. But this was so bold that all the experts in the field didn't even believe it. Right? So it's one thing to say, oh, I can't prove that because it's too hard. It's another thing to say, oh, that's ridiculous. Right? That's the most absurd thing I've ever heard. And that was the initial impression of this, right? Is really saying that elliptic curves are modular. So I do know from my reading that Sarah and Veal, neither one of them believed it. They said, I think Veal, I believe he said, I have no reason to believe it. I have no reason to disbelieve it, right? I mean, that's kind of an easy way out of it, right? I don't believe it's true. So this conjecture, as Shimura would say, Taniyama was somewhat of a sloppy mathematician. Sometimes he didn't assert things in a very, very good way. I don't know much about Taniyama taking his own life, but he died just a few years after stating this conjecture, but his conjecture would live on. And his close friend Shimura refined the conjecture. He knew exactly what he knew exactly what Taniyama was thinking about, so he made the conjecture more precise. So you can see that's 1965. So this is the actual conjecture, and it is known as the Taniyama-Shimura Conjecture. Today, it's not a conjecture anymore, right? So this is the way that Shimura refined it, is every elliptic curve over the rationals is uniformized by a modular form. So what that basically means is if you have this elliptic curve, so remember you have these solutions that live on the donut, then there is almost like a mate or a companion, right, in the complex half-plane of Poincaré with this weird hyperbolic geometry with all of its wonderful symmetries, that they're actually the same thing, right? So this is the way that this was refined, this conjecture. The wonderful thing, and you can see just how hard this problem is, these are some of the words used to describe what it would take, or do you believe that this conjecture could ever be called a theorem? Most people who were very, very close to this problem and knew of the intricacies involved said absolutely not. This will not happen in this century because this is just too difficult of a problem. All right, so I'm going to talk Barry Mazur's paper in the 70s. This is one where he generalized a lot of the work of Dedekind and also Kummer. So this is a very, very important paper that influenced a lot of people's work. Now, this is wonderful, because Frey in 1984, now correct me if I'm right, this is just a year or so after Mordell's conjecture was proved, right? So that's, you get a sense of the time here. So Frey has, and literally, a crazy assertion. This is totally wacko, right? So he claims that if someone proves the Taniyama-Shimura conjecture, guess what? Fermat's last theorem follows. It's automatic. And so now we think of Taniyama-Shimura as this impossible problem, but it's in no way evident that this conjecture has anything to do with this very, very old problem, right? Fermat's last theorem. Ken Ribbett at UC Berkeley, very, very familiar, brilliant mathematician in number theory, he was looking at his calendar like, is it April 1st, right? Is this a joke? Because there's no way that this implication is true. But what Frey did, the logic behind Frey's work is absolutely fascinating. So it's a little bit difficult to read. The first one here says, assume for a moment that Fermat's last theorem is false, right? So what that means, second frame, is you can find three numbers, A, B, and C, for which the equation is true. It might be for n equals 362, but it doesn't matter. You have the three numbers, A, B, and C. So what that would mean is that a specific elliptic curve, right? This is something that is associated with that solution, right? With that order triple. But this curve, Frey claimed, would be so weird, right? So strange that it couldn't possibly be modular. And now if you look at the last one, then that means if Shimura Taniyama were true, this would contradict that. So the logic behind this is absolutely fascinating, because this is known as proof by contradiction in mathematics. So what you're going to do is to assume the contrary, and if you end up with something absurd, then that means your original claim, right, must have been false. So this would mean that Fermat's last theorem would have to be true, but notice you would need Taniyama-Shimura. But remember, Ken Ribbett says, no way, this is a joke. Now, something I should mention before we go forward is there's a problem, because Frey's statement hasn't been proved. It's a conjecture. Holy moly. So to prove Fermat's last theorem, we are two conjectures away, right? So the first conjecture says Taniyama-Shimura implies Fermat's last theorem. But guess what? Taniyama-Shimura is a conjecture, right? That all elliptic curves are modular. So you have two pieces left, right, to actually complete this puzzle, right? So anyone want to guess who is going to prove Frey's crazy assertion? It's going to be Ken Ribbett. He thought it was a joke, right? So, and it wasn't but a year and a half or 2 years later, right? So he was initially the one that said this is a practical joke. But then when he reflected on it, he thought to himself, like, I've actually had some of these exact ideas. So it didn't take him long. He got, I believe, a little bit of help from Barry Mazur, but then, boom, it fell right into place. So as soon as that happened, guess what? Now you can see the picture. There's literally one piece left in this puzzle, and that piece is Taniyama-Shimura, right? Showing that all elliptic curves are modular. Enter Andrew Wiles, right? So Andrew Wiles read about Fermat's last theorem at the age of 10. So this was like a schoolboy's dream. He read about the theorem and said, I'm going to do that one day. So when he got news from a friend that Ken Ribbett proved the Epsilon conjecture, he became electrified because he knew exactly what that meant. All he had to do was prove Taniyama-Shimura, and that Fermat's last theorem would follow as a direct result of that. So in 1987, he begins work on this. He puts all of his other research aside, and he uses all of these sophisticated methods of those that came before him, right? All of these mathematicians here. He mentions that he was very, very motivated to do this because he said no one has any idea where to start, right, with Taniyama-Shimura, but neither did he, right? So he was completely working in the dark. So 1987 is the year. So I'm going to tell you a little bit about what Andrew Wiles did, because usually the summary of the story is that he spent 7 years in his attic, right, solving this problem. That's sort of true, right, but he got a little bit of help. So we need to show that every elliptic curve is modular. So his first idea ran 2 years, and this is why I was saying to people out there, you know, don't complain about your math homework, right, because it doesn't take you this long. So he spent 2 years, and he said, what I'm going to do is I'm going to count the elliptic curves and count the modular forms. And then if I can show that there's this one-to-one relationship, that there's the same number, that's going to mean that they're actually the same thing. So Wiles had two realizations when this happened. One was good and one was bad. So the good one is that he found he only needed to prove Taniyama-Shimura for a special class of elliptic curves, those that are semi-stable. So that really shaved off some of the labor that he had to do. But the other thing is he was working in the infinite. So you can't count things that are infinite. So he was trying to compare an infinity here with an infinity there. It just wasn't going to work. So his second idea, he worked on this for 1 year, is he was going to transform the elliptic curves into Galois representations. So we're hearing about Galois theory. Now what Galois representations basically do is they transform from the infinite into the finite. So it's a transformative tool that he was able to use. So if he was working with bundles of elliptic curves, he could actually count those bundles and see if there was a one-to-one association with the elliptic curves and the modular forms. But guess what? He gets stuck. Right? So Wiles was an expert in number theory, specifically Iwasawa theory. This was his area of expertise. He did his doctoral dissertation in this area. But the place where he got stuck is in the counting phenomenon. So there's something called an Euler system that needs to be developed to get a class number formula that will help you count the Galois representations. This is where he became stuck. So he heard from his former dissertation advisor, John Coates, and John Coates said, guess what? I have a student, Matthias Flack, who's actually working on this thing right now. And Andrew Wiles saying, this is perfect. This is exactly for me. So what he decided to do is he abandoned the Iwasawa theory, and he said, I'm going to immerse myself in the Floch theory. And Floch was using some work from the Russian mathematician Kolyvagin, right? So they were coming up with this class number formula that would allow Wiles to actually count the elliptic curves against the modular forms. But we are all human, even Andrew Wiles, right? So this was not his area. So he got stuck. And he realized at this point he needed to get some help. He needed to talk to someone. So remember, 93 now, this is 6 years that Wiles has been working pretty much in isolation. He's a very private man. He was doing his work, but he didn't share this with anyone else. He didn't tell anyone that he was working on Taniyama-Shimura. So he confided in a colleague, Nick Katz, and he said, I just need to tell you what I'm doing, and I need some help. But he didn't want to arouse any suspicions in his department that he was working on Taniyama-Shimura. So what they did, it's a little sneaky, but I like it when I hear it, is they formulated a special topics course with a innocent-looking title. And so graduate students would sign up for this course. And of course, Nick Katz signed up for the course, right? He was in the audience. And basically, this course was a cover, just so that Andrew Wiles could go through line by line his logic with Nick Katz. And Nick Katz was an expert in this area, so he could verify and validate everything that Wiles was doing, because Wiles needed help. So you can guess what happened to the grad students, right? So they're like, after a week, I'm out of here. Maybe I need to drop out of school, right? No one understood what Andrew Wiles was talking about, except that gentleman sitting in the front row, Nick Katz. He understood everything. So it worked exactly as planned, because after a few weeks, it was just the two of them. And they had their space and their time, and they continued to run the course. And Nick Katz would verify everything that Andrew Wiles did, right? So he was going through and doing this. So towards the end of the semester, they were this close. There were a couple of classes or a couple of bundles of elliptic curves that they could not prove to be modular, but they had all the other ones. So enter Peter Sarnak. So he had to get some more help. So he had to confide in another colleague. And so now they're very, very close. I believe there was one specific bundle that they could not prove modular. And guess what? It's that paper again, Barry Mazur, right? So Wiles was influenced by one particular statement in Barry Mazur's paper where he could transform those elliptic curves into a different group that he had already proved modular. Holy moly, right? So all elliptic curves are modular. What does that mean? You can see all the exclamation points, right? This is the day. So Taniyama-Shimura is true. It's not a conjecture, it's a theorem, right? The Frey curve that is so weird can't possibly exist. The solutions to Fermat's equation, you cannot find them. Fermat's last theorem follows because the Epsilon conjecture was already proved. The proof is not short, very, very long. So this is amazing timing because John Coates was holding a conference in the UK, right? And he asked Andrew Wiles, he said, hey, do you want an hour to speak? Do you have anything interesting to talk about, right? And Andrew Wiles said, can I have 3 hours, right? And John Coates remarked on this that was a weird thing that he said because normally he wouldn't ask for that. So obviously, sure, you could have 3 hours. So we'll give you 3 lectures, right? This was the title of his lectures: Modular Forms, Elliptic Curves, and Galois Representations. So there's no mention of Fermat's last theorem, right? So the first lecture, I remember reading, it was fairly poorly attended. Not many people came to his first lecture. But at the end of that lecture, obviously, there were some rumors that were swirling because he was using these really advanced, absolutely crazy techniques, right? So that led to the second lecture being fairly packed. So a lot of people came to that one. And those who were very familiar with the problem, they said, oh boy, this can have only one climax, right? He's going to prove Fermat's last theorem in the third lecture. So people would approach Andrew Wiles at the end of the second lecture like, hey man, where are you going with this? Come to my third lecture, you'll find out, right? So you just put the chalk down and go. And so at the end of the third lecture, at the very, very end, he proved Taniyama-Shimura, wrote down briefly Fermat's last theorem, and that was his final statement of lecture 3. And this proves Fermat's last theorem. I think I'll stop here. Right? So obviously there was a moment of stunned silence, and then of course, raucous applause, probably cheering, cameras flashing, high-fiving, right? Fist bumping. If you've never seen Mathematicians Party, right, then you don't know what you're missing. Right? Because this was the problem, not of the century, but of the centuries. This is the hardest mathematical problem ever. Right? And these people were in that room to witness this. I have some bad news. Okay? So Wiles took a risk. And what he did is he presented this at a conference. What would typically be done is if you have a new mathematical result, is you're going to send it out for peer review. You're going to send it out to the experts, and they're going to look at it and say, yep, that's right. But Wiles said, I'm going to do this at the conference. So one of the people that reviewed his result was Nick Katz, the man that sat with him in that room. But they both missed one little step in the proof. It was something that could not be fixed. And it had to do with the counting of the Galois representations. So Nick Katz would question Andrew Wiles, but he was never satisfied with the answer. But just at the point when Nick Katz was saying, I've got a problem with the step in the proof, people from around the world who were also reviewing the theorem found the same problem. They said, this is a problem, this is flawed. So it turns out there was no Euler system, no class number formula. You couldn't count the Galois representations. And you know that this happens in mathematics, that it's really like a stack of cards. If one thing is false, it just all comes crashing down, right? So Taniyama-Shimura was not proved, right? There was a flaw. So fall 1993 was a very dark time for Andrew Wiles because he was on top of the world. After he had proved Taniyama-Shimura, this was front page news in the New York Times and the Washington Post. Us mathematicians, we rarely get the front page, right? So that was a big deal, right? So his colleagues would look at him with a mixture of hope and pity. And as I was telling some people, this is not one thing where you pass Andrew Wiles in the hallway and you say, hey, how you doing on that theorem? Did you get it yet? Because this is something where you don't talk about it, right? It was such a difficult time for him. So one of his former students, Richard Taylor, I believe he took sabbatical. He said, I'll come work with you in the fall. We'll fix that proof, right? We'll patch it up. But fall went by and still nothing, right? So they weren't able to do it. Okay, so this is one of the biggest days in the history of mathematics. September 19th, 1994. It's about a year after when Wiles returned, right? His somewhat difficult state. So what Wiles said is, he said, I'm done. I'm going to give up, but I owe it to myself to know why this is incorrect. What is wrong? So when he was looking over his work, I believe this was a Monday morning, it suddenly hit him. He said, or what he discovered is the exact thing that was making the Euler system fail, right, was precisely what would make the Iwasawa theory work. And if you remember, Iwasawa theory is what he abandoned 3 years ago. So this is what he threw away and then leaned on the work of Matthias Flach and Kalavagin. But this result was so profound that he describes this as the single most important day of his professional life when he discovered this. So he looked at it, and the mathematics behind it was so beautiful that he said, this couldn't possibly be wrong. It can't be wrong. So he scribbled something, and he obviously went for a walk. That's what you do, right? You go for a walk. Then he came back, and he looked at his desk, and it was still there, and it was still right. So he said, I gotta sleep on this. So he went home, because obviously he had already failed, right, in front of the world. You know, he has to be very careful here. So he came in the next morning and looked at it, and this is positively, absolutely correct. And so he wrote it up. He gave Taylor the credit because of all the help from the previous fall, and then he submitted it right to a referee journal, and they all agreed. This is positively, absolutely correct, right? So Fermat's last theorem was put to rest. And so you can see that there, my mind is now at rest. So it took him about 7 years to go through with one major, major failure to prove Taniyama-Shimura. And Frey, who came up with the Epsilon conjecture, had said, he credits Wiles because he mentions that Wiles was one of the only living mathematicians in the world who actually believed that Taniyama-Shimura could be proved. Because remember, if you look at the adjectives that we saw before, impossible, impenetrable, this is a problem that can't be solved. Andrew Wiles believed it could be solved, and he solved it. So some of the afterthoughts, some things to think about, right? Because people ask these questions. Did Wiles prove Fermat's last theorem? Sort of, right? So he proved Taniyama-Shimura conjecture, which led directly to Fermat's last theorem. But you could tell there was a lot of other mathematicians that fed into this result, right? People will always ask, is a simpler proof out there? Because this is a proof that most people cannot understand. And if we think of Fermat and of his honesty and the fact that he was a fantastic mathematician, it is possible that a simple proof might be out there. Ken Ribbett hints at a totally different way of solving Fermat's last theorem without using Taniyama-Shimura conjecture. And I'll come back and mention faultings, because when Wiles failed that first time in '93, many mathematicians feared that faultings was going to beat Andrew Wiles to it. But he didn't, right? And Wiles got it. The third question is the burning one, right? So did Fermat have a truly marvelous proof, right? That one that he couldn't fit in the margin? It depends on who you talk to, right? The people who worked on this theorem would say, no, he couldn't have possibly had a proof. But he might have had a very, very different way of doing it. So I'm going to tell you, on a much, did I say much? Much smaller scale, there's this inequality in mathematics known as Bernoulli's inequality. And it has, I don't know, many, many different ways of proving it. But in a journal, I think it was last year, it was either 2015 or 2016, in the College Mathematics Journal, there was a short article that was 6 lines long on one page. And the title of it was, A Very, Very Elementary Proof of Bernoulli's Inequality. So this is an inequality that has been proved time and time again, but no one had come up with this one proof that was 4 lines long that involved algebra, right? So that will always be the question that you think about. You don't know what Fermat was thinking about. You don't know his way of approaching the problem. But the fact that he tried it for 3 and 4 and didn't do much else, that's a little questionable, right? What we do know is that Fermat did not have the proof that we know today, the 1995 proof, because all of that mathematics didn't yet exist, right? So he didn't have access to that mathematics. Some people ask about the practical application. I was mentioning this outside. Number theorists love to live in their heads. I'm not sure if Fermat's last theorem has specific applications, but so much of the mathematics, the theory of ideals, right? Ideal numbers, they have many, many applications and have opened up many particular domains of mathematics that are used in fields that are strictly known as applied mathematics. So these are some of the references, because as I mentioned, as I told some of you outside, I know only what I read about this theorem. It's a fascinating read. There's a very short book, reference number 1. It's only about 130, 140 pages, a quick afternoon, and you'll know a whole lot about Fermat's last theorem. This talk is pretty much a Cliff Notes version of that. If you like videos, the PBS documentary, right, you can see how emotional Wiles actually gets. He actually tears up when he has to talk about his epiphany, right, that morning of September 19th, 1994, because that was so profound for him to actually realize, I have solved this problem, I have a solution. And the last slide here is my only photo, but one of them is Andrew Wiles, and the other one is Fermat, and I'll let you figure out which one is which. Right? Because there's a lot of years that separate them. And so I have a couple of things if you want to hang around. There's this book on modular forms and Fermat's last theorem. This was a conference held in Boston shortly after the theorem was proved. So it's like a monograph that contains a lot of the papers that were involved in proving the theorem. And this is wonderful because this is the paper that was submitted, the corrected paper due to Andrew Wiles and Richard Taylor that was submitted in 1995. So if you flip through this, you will find a short statement. I can't tell you what page it is, because it's about 100 and something pages, where it says all elliptic curves are modular. You can see the statement of it, and then obviously you see the proof. So if you want to flip through this, I can't explain much of this to you, right? It's very, very deep mathematics, but it makes for a good story. That's all I have. Thank you very much.